All right. Yeah, very good morning to all of you. Yeah, thanks for coming to our session entitled Session Identifiers Are For Now, Passwords Are Forever. Cross-site scripting based abuse of browser password managers. My name is Ben. This is Sebastian who's gonna, we're gonna switch back and forth during the talk. But before we start and actually introduce ourselves, I first have a question. And this is something that kind of gets your blood flowing early in the morning so you don't fall asleep during my talk or our talk. Show of hands, who's using Chrome as a browser? I figured as much. Firefox. Okay. Safari. Oh, still. Opera. Yeah, you're like 1%, I think, of the internet users. And finally, who uses Internet Explorer? Awesome. So during this talk, or at the end of this talk, you'll actually go away and think of Internet Explorer in a way you have not thought of it before, because it's, as we will show you later on in the talk, it's actually, for our attack scenario, it's one of the most secure browsers. But in terms of full disclosure, I have to be honest. Okay, this is broken. Awesome. I was actually an intern with Microsoft Research until last week. This is also why I'm wearing this T-shirt. So if I say anything nice about Internet Explorer, they still owe me kind of a paycheck, I think. So yeah, that's why I have positive things to say about IE. Okay, quickly, just something about us. So I already said my name is Ben Stock. I'm a security researcher and PhD student at the university in Erlangen in Germany. This is Sebastian Lekies, also PhD student at the university in Bochum. And this is joint work with our colleague Martin, of whom you see half down here. He's working for SAP Research. Actually, all three of us used to, at some point, work for SAP Research in a distant past. And we still work together and collaborate on quite some stuff. Okay, so about this talk. In this talk, we'll actually present to you the results of an analysis of different browsers, so browser-based password managers. We're not going to talk about 1Password or LastPass, but basically about the password managers that the normal user can use, such as, all of you guys just showed hands which browser you actually use. We will then, or Sebastian will then demo kind of this analysis and show how bad they really are and how great IE is in comparison. We will then go on with a study of what password fields look like on the web, which is also pretty scary. And in the end, we actually, after all these scary parts, we say, hey, this is super insecure, everything. We actually have a potential solution towards this problem. But before we start, let's step back one step. And look at what is cross-site scripting. I guess most of you guys know, but I have nice cat pictures on here, so I still want to do the slides anyway. The web's principal security policy is the so-called same origin policy. And the question is, why can't an attacker, say having the domain attacker.org, read the visitor's emails so if somebody visits attacker.org, why can't he actually read the Gmail emails? And this is precisely the same origin policy's job. It makes sure that resources can only get access to one another if their origins match. And an origin, in this sense, is defined as the protocol. So, for example, HTTP versus HTTPS. The domain, whereas this is actually subdomain, not just second-level domain, as well as the port. So only if these three things match, then the access is granted. And this actually makes the job a little bit harder for an attacker, and it makes him very sad. And he also has a very sad kitten in this instance. So cross-site scripting, what is the actual underlying problem? Web apps process data. This is a very obvious statement, I guess. Otherwise, it wouldn't make sense. Otherwise, we just have kind of the web as invented by Tim Berners-Lee, where you just have content you can see, but you can't really interact with the web application. And this data is somewhat produced or provided by the user. This might be login credentials. This might be something you post in a forum, anything like this. And basically, all that actually reaches the server via HTTP, which is basically post parameters, it might be get parameters, it might even be headers, it might be, whatever, however a user can interact with the web application. And the web application then somewhat processes this data. It might either store it, or it might kind of, return it back directly. Think of a search query where you enter something into a search field, and then the website says, hey, you searched for your query string, and then uses also this kind of data not only to reflect this back to you, but also do the search in the background so you can interact with it. But actually, if you look at this little snippet of data. I hope you can all read it. Basically, this script alert 1 script closing is actually not data, but it's code, right? Because the browser, if it sees something like this, says, hey, this is a piece of JavaScript, so I will now execute it and open this alert box. And the important thing is that it's actually interpreted by the victim's browser in the context of this vulnerable web application. That means, think again about the same origin policy. If I, as an attacker, am able to inject my own code into gmail.com, then actually I'm running in the origin of gmail.com and I can actually read your emails. And yeah, the idea is, first of all, you try to find a flaw in the web application that allows you, as an attacker, then allows you to put your malicious code there. You obviously test this in your own browser to begin with. And then you somehow make the victim visit that site. That might either be by kind of click or sending them spam. Obviously, if you think about reflected cross-site scripting, where this is part of a get parameter or something, this URL might be super long, so it might be very obvious what you're doing. But what you can also do is, for example, register a domain like kittenpics.org, which we actually own, post nice cat pictures on it, and while the user is happy that he's watching cat pictures, you actually have a hidden iframe on the website. That kind of contains this URL, so the user is never aware that in the background, while he's looking at cat pictures, actually I'm loading gmail.com with this whole bunch of malicious payload. So basically, in the end, we can read your Gmails. Okay, so I spoilered listed already a little bit. What can a cross-site scripting attacker do? So the first and foremost thing you will always see if you see a proof of concept for a cross-site scripting exploit, people open alert boxes. And this is like, wow. Obviously, kind of very freaky hacker stuff going on here. But actually, the attacker can do much more than just open this alert box. He can, for example, hijack a session. That means he can force the victim's browser to kind of leak the cookies that might be involved. It might force the victim to click on a link. For example, I don't know, or post something. Think about a cross-site scripting on Twitter, where what I'm talking here actually, I said, hey, visit kittenpics.org, and in the background, actually, the kittenpics.org is loading Twitter, plus this malicious payload, and then all of you posted, hey, this is an awesome talk going on here right now. It can also be used to alter content. There was actually a case of the German Chancellor, of the Chancellor's website, where there was a cross-site scripting, I think also in a search field, which eventually led to some fake content, namely Chancellor Merkel resigned because of, I don't know what it was, but I think it even made it to the news, just because, it was actually on that website. You can spoof login forms, but first and foremost, and this is also the topic of our talk, and this is something that typically users or kind of researchers don't necessarily think about, we can actually utilize cross-site scripting attacks to steal your password manager's passwords. So basically, just to give you a quick overview, I think in literature, also in the security community, people typically speak of 3 different types of cross-site scripting. We actually make the distinction kind of on 2 axes. We can either have client-side or server-side code that causes the issue, and then we can have reflected cross-site scripting where kind of data is directly echoed back to the user, or we can have stored cross-site scripting if you think about a forum post. Exactly. But then again, isn't cross-site scripting like, hasn't it been solved, especially with the content security policy and things like this? Actually, it has not been. So for last year's CCS, we actually conducted a study that showed that about 10% of all the Alexa top 10K websites carry at least one DOM-based cross-site scripting vulnerability. This is a class of cross-site scripting that has not been researched all that well in the previous years. Then again, as you might know, and basically all of you, or a lot of you said you use Google Chrome. Google Chrome is shipped with the so-called cross-site scripting auditor that actually tries to detect and block cross-site scriptings. But turns out that, basically for our Black Hat US talk a couple of months ago, we showed that about 80% of the domains out of these 10% of the DOM-based cross-site scripting domains are still vulnerable even if the cross-site scripting auditor is deployed. So it's not really a kind of a good way to block this. And this is also kind of underlined by the White Hat security report. And it again says cross-site scripting regains the #1 spot after being overtaken by information leakage. So again, last year, cross-site scripting was kind of the most prevalent kind of vulnerability on the web. Okay. And with this, let's switch over to Sebastian. Come back in a minute.
Okay. Oh, this is working. Great. So after we now have the foundations that we need to understand the rest of the talk, I would like to talk about passwords and password managers. So we'll first look about how passwords are used on the web, and then a little bit how password manager works and what are the security features that password managers have. So if we look at passwords on the web, we have to state that passwords are still the first and the only form of authentication on the web. So we basically only use passwords on the web. And well, in a perfect world, I guess we would not have passwords. We would have something that is more secure, that cannot be stolen, that we do not store in databases and so on and so forth. But we still have the passwords all over the place. And well, in a semi-perfect world where we still have passwords, we would have a password for each site. So, and this password for each site should be sufficiently complex to avoid brute forcing and hash cracking and so on. But the reality looks a lot different. So here we see a few statistics that we've taken from other researchers from the web. And what we can see is that, so what the researcher did, he analyzed password dumps of hacks that were publicly available and checked what kind of passwords are people using. And what we, for example, see that is 5% of all users just use the password. Then we have about 10% of the users either use password, 1, 2, 3, 4, 5, 6, or the numbers of 1 to 8. And what we also see is that a lot of users use the same passwords. So if we compile a list of the top 1,000 passwords, we see that 91% of all the passwords are used from that list. So it's pretty easy to crack passwords. And in recent years, we saw a shift from big internet companies to enforce more strict password complexity rules. And this is illustrated in this comic somehow. So if you look at Facebook and if you look at Google, we see that those services require much more complex passwords. So we need to use uppercase letters, lowercase letters. We need to have numbers and special chars in your password. And this makes passwords very hard to remember. And this either leads to a very unfortunate situation. People are reusing passwords. And it's not the semi-perfect world where we have a sufficiently complex password for every site. And one solution that was introduced lately in browsers are password managers. So because password managers take the burden of the user for remembering the password. But the password manager will do this. And nowadays we see that all the browsers that Ben presented in the beginning have password managers. And if you try to store a password, you will see such a dialog that says, well, here, would you like me to remember your password? And if we look at the functionalities of such a password manager, it has basically two. The first one is to store the credentials on first submission when you see that form. And I think a lot of people have looked into how this is going and if this is secure and if malware can extract password from the computer and so on and so forth. But not a lot of people have looked at the second functionality. And the second functionality is inserting the credentials into a web page on a subsequent visit. So when you come back to the website for which you stored the password, it will already be filled into the form in most of the password manager, and you just need to click login. And this has severe consequences. So we would like to look at this second functionality, and we would like to look at this situation in terms of thinking about cross-site scripting. So here we have an example. So we have a simple login form, and we have a password manager. And the password manager has a password stored for this login form or for this origin. And what he does, he simply fills that form with a password. And although this is implemented in the browser, there could be special protections against attacks such as cross-site scripting. But what we see is that there is no protection at all. So the way this password is inserted into the form is that the password manager just puts the password into the document object, into the DOM, into the document object model. And well, JavaScript running in the page can access data that is put into the DOM. So JavaScript in the page is able to access the email field and as well as the password field and just extract the password. And here the XSS comes in. So what an attacker gains through XSS is execution of JavaScript code in the origin of the web page. And hence, he's able to execute XSS JavaScript, and therefore is able to access the password field and extract the password. So I will demonstrate this shortly. It's very easy and very straightforward. So here I have a page. It's called login.com. This is a page. It's not real login.com, but it's a page on my local computer. And what we see is that I stored a password in the password manager. And we see that this is Chrome. And if I reload this page, Chrome will automatically fill in my password into the form. So let's have a look at JavaScript. So I just opened the JavaScript console where I can execute JavaScript commands, such like a cross-site scripting attacker would do. And what we can just do is we can select the password field. So I use just a JavaScript method that is well known and say, well, give me all fields named password. And this gives me a node list. So I take the first element. And here I can see the HTML code of the password field. And we do not see the password in the HTML, but we can just query the value attribute. And here we see the JavaScript can access the password that was inserted into the page. Whoop. Ben says I should zoom so that it's more visible. Yes, that's a good idea. Okay, so here we can see the password is extracted in clear text. And this is a very bad thing if we think about cross-site scripting. And in order to see what the security consequences of these features are, I would like to compare two worlds. One world without password manager and a world with password managers that enter your credentials automatically into form. So in a world without password managers, XSS attacks only work when the user is authenticated. So what you would like to do in an XSS attack is you would either like to conduct state-changing actions in the name of the user, or you would like to steal the session credentials, so the session cookie, to conduct some state-changing actions in his name on your computer. So if you conduct an XSS attack, you construct a URL with the XSS payload and send it to the victim to execute. And the attack only works when the user is authenticated. So if he's not authenticated, you cannot conduct any state-changing actions, and there's also no session credentials to steal. In a world with password managers, an XSS attack just works out of the box. So if you visit the page, the password manager will fill in your password. You have JavaScript execution on the page as an attacker, so you can just access the password, and you can steal the password. And the consequences of this are very bad, because in a world without password managers, we can just steal the session credentials, so the session cookie. And the session cookie is only valid for a very limited amount of time. So as soon as the user logs out or a timeout is hit, the session credentials are not valid anymore, so the attacker cannot conduct any further actions. But if you have a password stolen, the attacks are limited to the lifetime of a password. And usually, people will not notice that they have been accessed, and so you have the password of the user, and the probability that he's not changing this password is very high. And then another problem comes in. So passwords are often reused by users on other web pages. So an XSS attack on password managers do not only affect the site that the user is currently visiting and that is vulnerable to XSS, but it will affect all the sites that the password is valid for. And if we look at this, we have to state that, well, the current password manager generation makes XSS attacks more severe. So it's much more easier for an attacker to do something bad. And we took this as a basis for our research and had a look at security mechanisms in password managers. And as a spoiler, we didn't find a lot of them. But what we did, we found 5 key features of password managers. So how they are inserting credentials into field. And we will have a look at how password managers are matching the URLs and the forms that they insert passwords into. We will look at password managers that require user interaction before filling in a password. And we will also look at the autocomplete attribute. So let's first look at URL and form matching. I have another demo. So here we are in Chrome again, and I stored passwords on this website, so on login.com/loginphp. And on this very same domain, I have another page, which is called search.php. And search.php is a simple search application, so I can just put in some value, and it will search something for you. And here, obviously, there's a cross-site scripting. So here I have user input, which is reflected in the get parameter and reflected in the page. And I can just enter some arbitrary HTML code. So for example, I can just put B so that you believe me. So we see that the code that I put into the URL is reflected in the page. And now the text is bold. So let's just try to be a cross-site scripting attacker and enter a form here. So I just add another form. And I give 2 input fields to the form. So I say just, well, I would like to have a text field. And I give it just an arbitrary name. And now I will add a password field and just give it another arbitrary name. And then I send this, and I see my form, and I see, well, Chrome isn't very intelligent, so it just say, well, I have credentials stored for login.com. Here is a form. It has a password field, so I enter credentials. And the funny thing is I can even add a third or fourth field just with another name. And Chrome will just enter the password. So Chrome has no matching rules at all. So it just stores the password, and as soon as it sees a password field, it will enter your credentials. And as a cross-site scripting attacker, I can now just add some arbitrary JavaScript into the URL, and then just extract that password from that form, as we have seen it before, and steal your password. So here we can see a small overview of browsers doing matching of URLs and forms. And the only browser that really does a matching is the Internet Explorer. So Internet Explorer only inserts credentials into the page that you stored the credentials for, and only into that single form. And all the other browsers just fill in passwords into any form that is present on the web page and that has a password field. The next feature that we noticed is user interaction. So as we saw in Chrome, passwords are just inserted into the page without any user interactions, and that makes it very easy for an XSS attacker to automate the attack. So he just needs to send his cross-site scripting attack and will receive the password. So we'll have another demo, this time in Internet Explorer. And here we see the same site. It's login.com/login.php, and I store the password on this site in IE. And if I refresh this page, takes a while, we will see that there is no password in the password field. Well, why does it take so long? Sorry for that. It's on the local host, so it should. I'm not sure. Trying. Okay. No, it's still showing loading, but. Okay, let's just wait a few seconds. Okay, I'm not sure what's going on. Okay, I switched to another browser. So I just did Safari. So here we see the same site again. And if we visit it with Safari, we immediately see that there is some kind of pop-up window. And we first need to click until the password is entered into the form. And if the form is, so I can empty it again. So it will, if I click. So there's some kind of user interaction involved. So if a cross-site scripting attacker wants to exploit you, it's not that easy. So he somehow needs to make you to click on that thing. And here in Safari, we see a very good example of a secure user interaction, because this thing cannot be hidden by other things. So an attack that you could choose to overcome this issue is clickjacking. So you could try to make the user click on this thing, and you could try to hide this window from it. But in Safari, it's realized very good. So this pop-up that you see cannot be overlaid by any other site or by any div elements or that you have on the page, and it cannot be made invisible by. Yes.
It's not in the DOM then.
Yes, it's not in DOM. I can show it. I have a short. I say it's a very good solution. So in this case, it's not click checkable. So here we can see it. Here I have a page that is called evil.com, which could be used by the attacker. And he framed the login.php page from login.com. And here you can see it. I made it opaque, but still so that you can see it. And this thing is still showing up, so people will notice it. And click checking this is very hard. OK, let's have a look at the overview again. So the reason why I wanted to show Internet Explorer is because at the time when we conducted this research, Internet Explorer was the only browser doing that. So before, all the browsers just filled in the passwords. And in the last 2 or 3 months, Opera and also Safari changed its behavior to show that box. OK, so let's have a look at another feature. So in HTML5, we have a new attribute that is called autocomplete. And here is some text of the specification. And if you put autocomplete to a text field, it has either 2 meanings. So it can either be used for input fields that have a particularly sensitive data. For example, the activation code of a nuclear weapon, says the specification. Or you have something that the user needs to re-enter every time he visits the page. Something like, for example, in a one-time password for your banking account. So the autocomplete attribute can be used for a page to opt out of storing data in the browser. So you can tell the browser, don't save this data. It's sensitive. So we had a look at the different browsers and if they adhere to this attribute, if you put it to the password field. So if put to the password field, browsers shouldn't store your password in there. So let's have another look again at Chrome. I have another page on this domain, and it's called autocomplete. And if we look at the password field, here it is. And here we have the autocomplete attribute, and we switch it to off. But well, Chrome simply decides, well, even if we try to submit a form, it will say, yes, do you want to store this password? And if you press yes, it will store it, and it will automatically fill this application. And there's an interesting other example. So we have Firefox, and here we can see login.php, and the login form will be automatically filled by your password manager. But if we go to autocomplete, we will see it will be not field filled. So it somehow adheres to the autocomplete field, but it still autofills if you click. So if you have the autocomplete feature in Firefox, it will just switch to a mode where you require user interaction. And then it will again autocomplete the field if you click. So it will still store the password. So let's have a look at the overview again. So we have Chrome, which doesn't adhere to that attribute at all. We have Firefox and Safari. They somehow adhere to it because they do not autofill the password field, but they still autofill it if you click. And then Opera also does not adhere to the attribute, and Internet Explorer adheres to it and does not offer to autocomplete the field at all. So we reported this to Google. So we opened a bug and said, well, if the autocomplete is present, the autocomplete attribute, we should not store passwords and do not autofill the passwords. So we opened the bug and told this Google, and well, Google replied, well, this is intentional and working as intended. So basically, they do not really adhere to the spec and does make users somehow exploitable. And if we look at all these features, we somehow see a trade-off between usability and security. So it would be very secure to not fill the passwords, to have user interactions where the user has to click multiple times to avoid attacks. But I think a lot of browsers are taking the usability route. So it's very convenient that the password is in your password field and you just can press the login button that you do not need to click. And I think that the autocomplete attribute is also a very good example for that. Because if the web page specifies autocomplete equals off and your browser does not store the password for you, users will blame the browser for that. They will say, well, Chrome does not store my credentials, although I would like to store them. So Chrome just says we ignore the wish of the web page to not store these credentials. And with this, I would like to hand over to Ben again, who will talk about the state of password fields on the web.
Thank you. Just one addition to this guy. Actually, if all fields in a form are set to autocomplete equals off, then they don't store it. But the notion that I would have as a programmer, think about the following. I have this form that was previously, where the password manager previously stored the credentials, and now I want the credentials no longer to be stored for that field. Then I don't want the password to be stored, right? So I set autocomplete to off for the password, which means, as the spec says, dear browser, please don't save it. In these cases, if there's at least one field in this form that doesn't have autocomplete set to off, then Chrome stores it. Only if all fields are set to autocomplete equals off, which programmers, I think Google thinks that programmers go ahead and by accident put autocomplete equals off to a form. And in these cases, they want to help the programmer by storing the password. But yeah, again, I mean, this bug report that we opened was kind of shot down with this very interesting comment, not really commenting on the fact that they are violating the specification here. All right, so enough Google bashing. Again, I'm still wearing my Microsoft hat slightly. So another part of the research we did was to then look at what password fields actually look like on the web. And this is actually was done so we could gain a better understanding of how sites handle forms. So for example, how many sites are actually trying to actively opt out of password managers storing their passwords, even if they not necessarily do that. So looking at kind of fields that have autocomplete set to off. And also, for example, look at the XFrame option setter, which is now deprecated and has been overcome by a CSP directive. Actually, the XFrame option setter can be set by a website to tell the browser this site should not ever be framed. Sorry. So if we think about the following, think about a combination of or a modification of IE. IE does not fill the form if it's not the exact right URL. So if we think back to our example where we have our search field, the search field's URL does not match the login forms URL. So what an attacker could do is he could use this cross-site scripting on the search field to inject an iframe, and then try to force the browser to fill out the credentials there, and because they are both the search field as well as the login form, they're in the same origin, the outer side can access the iframe and can then access the password. So we also wanted to see how many sites actually make sure that their login page cannot be framed, so by setting the XFrame option setup. To do that, we implemented a very simple crawler, which basically goes to some domains, in this case the Alexa top 4K. It scans the entry page for a login field, but as I guess most of you know, not every web page necessarily has the login form directly on the first page. So what we did is kind of look for indicative keywords like login, sign in, and such. We only did that for English. For English words, so I'm not sure if we called all the Chinese login forms that might have a different URL or German is basically the same. And finally, a final piece of the puzzle was that this extension actually wraps access to fields, so that if JavaScript is actually trying to access this field, because this is a very interesting thing as well, we can notice that as well. And these are the results of this study. So out of the 4,000 websites, we actually found password fields on 2,143. And this is basically the 100% of this relative column, so this third column. So it turns out that even with this relatively simple approach, we were able to find password fields on half of the Alexa top 4K sites. Now for the scary part. So only 38% of those actually had the form on an HTTPS page. This is not that bad yet, because just delivering the form on an HTTP page is, well, not really an issue, because, well, then somebody can eavesdrop maybe on the connection. He will see, okay, there's a password field, but he can't really do anything with it. The thing that scares me way more is the fact that only 56% of the domains we found password fields on actually submit these passwords over HTTPS. So almost every second page actually uses plain HTTP to transmit your passwords to it. And if you think about what Sebastian said earlier, users typically tend to reuse passwords quite a lot. So it would be relatively straightforward and easy to get kind of passwords for a lot of sites just by being in the network. And I actually have there's actually a similar attacker model, which I will talk about in a minute. Then only 13.6% of all these websites actually had the autocomplete set to off. I think most of them only had it set to off on the password field. So again, Chrome just ignores this, still stores it nevertheless. And the final number here, 325 domains, somehow used JavaScript to access this field. I will talk to you about this a little later in the talk. But we see that this either means that, for example, most of the sites actually just wanted to check that the field was not empty. This was also JavaScript access, which we could detect because we had this wrapper around it. So a similar attacker model to what we did, and also research that was basically going on more or less in parallel to our research, was man-in-the-middle attacks. So for Usenix security this year, just two and a half months ago, I think, David Silver et al. Actually conducted kind of a study similar to ours, but with a different attacker model in mind. So they went ahead and said, okay, we will go to a public or to a cafe somewhere and offer a free Wi-Fi service, and everybody loves free Wi-Fi. And typically users say, hey, free Wi-Fi, cool, I'll just click on that and be happy with it. What they actually did is, into every HTTP connection they could find. So for example, I think Google is a bad example, but any HTTP connection, so not encrypted connection, they actually went ahead, intercepted the response, injected iframes into the site, for example, to whatever, Google, Facebook, and so on and so forth. And similar to the attack we described, the password managers, so to the login forms, sorry, the password managers would then, in these cases, fill out the forms. And since we have a man-in-the-middle attack, we can kind of put arbitrary payload in this response from Facebook or Google. So they also kind of put some JavaScript in there that waited, similar to our attacks, waited for the password manager to be as kind as to fill out the forms and then leak it back to the attacker. And they did that. I think they had like 10 iframes or something in parallel. So each time a user would visit a different HTTP page, they would just inject the next 10 domains into it. And according to them, it's very, very quick to automate, to kind of sweep, or they call it a sweep attack, where you just sweep over the top 1,000 domains, for example, and try to steal as many passwords as possible. But this is, Pardon? Well, it's not our work. But as far as I know, they didn't try to forge SSL certificates. I know of a similar study where, Well, if you think about the following, if you don't think about an HTTPS connection, but HTTP. Basically, if I do a request to Facebook.com with, say, HTTP, and we have a man-in-the-middle attacker. He can modify any headers he wants to. He can inject anything. He can just inject it directly into the page. So CSP doesn't help in these cases. And there was also a similar study where I think a group from another German university went ahead and also opened one of these public Wi-Fis, and they said, dear user, the only prerequisite you have to, or there's one thing you have to do so you can use our Wi-Fi. Please install this certificate, which was actually a root certificate, basically allowing them to sign arbitrary certificates. And still, I think like 90% of the users said, yes, I want free Wi-Fi. Give me free Wi-Fi. I will install anything you want from me. Because, also, it's not an executable or something, right? It's just a certificate. What do I know what a certificate can do? But yeah, so I know, I think. All right. So we have these two different types of attacks. So we have this cross-site scripting attacker. And one disadvantage that the cross-site scripting attacker has is obviously he needs cross-site scripting vulnerability on that target site. However, as we've seen, this is not that hard of a task actually, because most of the websites are still somewhat insecure. In contrast, one downside of this network attacker is, as you clearly pointed out, it does not work with HTTPS, at least not the way they presented their work. Whereas, again, the cross-site scripting attacker, if we have an XSS on an HTTPS page, we can just as well steal the passwords from there. But this is one case where the network attacker is way more sophisticated and powerful than we are. He can just eavesdrop on the credentials that are being posted to the website. So again, half of all the password fields are actually submitted via HTTP instead of HTTPS for some reason I don't want to understand, I think. So summarizing this, actually attacks against password managers can be easily automated. So bottom line of this is the default password managers, and let's not talk about IE here, not again. Default password managers in browsers are not really secure. This might be a different story for these plugins like LastPass and 1Password. But we have to think about, although I guess most of you here will not necessarily use the built-in password managers because, well, you're security aware. People on the internet typically are not that security aware, to put it mildly. So typically they say, hey, there's a feature in my browser that allows me to not remember my passwords. Awesome, I'll just use that. Why should I buy something or install something that I don't have the technical knowledge to actually use? And in our work, we found that we have issues related to all kinds of things. So we have this autofilling issue where basically all browsers actually say, hey, there's a password field or a form field. I'll just put in my passwords here. Some of them ignore autocomplete, at least partially. There is no verification that it's actually still the login form, so we can use foo and bar as names instead of whatever username and password. So it's also for us as an attacker very easy to kind of inject this arbitrary form or this very generic form into any website we want to steal credentials from. So the question is, and this is now the end of the attack part basically, can we come up with something that might be a better solution that can still be deployed in kind of commodity browsers where we don't have to rip out basically the whole password manager, as well as don't have to force the users, the untrained users, to learn how to interact with the password manager, that they have to click and so on and so forth. Okay. So what we've seen in our research is the idea of what a password manager should do is it should aid the user in authentication. So it should securely store the passwords, and if they are needed by the web application, he should then kind of provide them to the web application so the user can authenticate. And our notion of authentication is the credentials are being sent to the server. This is actually when you authenticate against the server. However, as we have seen, there is somewhat of a mismatch in this notion and the implementation of it. So the credentials are, at some point, sent to the server, but most importantly, before that actually happens, they are inserted into forms, and therefore inserted into the document object model and accessible by JavaScript or a cross-site scripting payload. And we just propose, well, let's try to align this implementation, how it's done in browsers, with this notion of credentials are being sent to the server. All right, so on the upper part of this slide, you actually see the way password managers work right now. So initially, we find a login form. Then the password manager comes along, scans the page, finds, hey, there's a login form. So I'll just go ahead and insert the username, the password that I stored for this site. And when the user then clicks on sign in, this password is actually sent to the server. Right, so this is obviously what we talked about all this talk. We now propose the following. Instead of the password manager directly inserting username and password, let's just go ahead and insert the username and insert some pseudo-random nonce into this field. With this nonce, the attacker can do absolutely nothing. This is just so that the password manager has a way of kind of figuring out, okay, nonce X belongs to password Y. And what actually happens is, if we now click on submit, since we're in the browser, we see this outgoing request with the username and the nonce. The nonce can be of any format so that we can actually easily detect it in the outgoing request, and that it can also not be there by accident, so just use something very long. What the password manager then does is, it just goes ahead, says, hey, there's a username, there's a password, there's a nonce, so let's exchange the nonce with the password. There are some constraints to this approach. So potential pitfalls for this would be, what if an attacker goes ahead, again, he has cross-site scripting capabilities, he changes the form's target. So instead of posting it to login.com/loginphp, he actually posts it to attacker.com or evil.com, dump PHP. Another way of going about this would be, for example, to post it to search PHP. We've seen that before. And think about the following. We're still in this scenario where the attacker has XSS on some site. He has this iframe that points to the login page. He just modifies the the target of the login page, hits send after the password manager has inserted the credentials, and now this search PHP reflects back what it was given, right? What he can now do, because he still kind of has control over this parent frame, which is allowed access because they're on the same origin to this iframe, he can then kind of read the content of the search page, which has reflected back the password, and could have then stolen the password. An attacker could also go ahead and just change the method that is used to post or to send the form, from post to get. Get means that all the parameters, all the fields in the password, in the form, are kind of appended as get parameters. So again, he posts the form and then just reads the URL of the page that it has now been redirected to, and then he has kind of a username get parameter and a password get parameter, and can therefore extract it. So we therefore propose the following constraints. There should be a very strict checking of the form target URL, so that the attacker cannot change this at all. And also, we propose only to exchange these nonces in post parameters and never in get parameters. We implemented a proof of concept implementation for Firefox. This is due to the fact that Firefox has a very nice API that allows you to interact with the password manager. So you can exchange stuff, you can delete stuff just from an extension. So we still have this default question that you're being asked. Do you want me to remember the password? This is the first stage. If you hit yes, remember the password, this actually goes to the password manager. And in the password manager, we have a callback that kind of then is called when a new password is entered. And this then calls our extension that we wrote with this information. So for which host was it stored, for which user was it stored, actually also for which URL, and what was the password. And what we do then is basically we store this secret password in our database, we generate a random nonce, and exchange the credentials that were initially being stored in the password managers with our nonce and the username. So therefore, the password, we still use the default password manager, but rather than storing passwords, it now just stores these nonces that we can access later on. This is a little tricky to read. Sorry for that. So yeah, this is an example of how it then goes along once we post a login form. So on the upper part, I'm sorry, it's very small. We have a post to login PHP, and this nonce is there in the data, so in the post data. Our extension verifies that login PHP is actually the page that this password was originally posted to. So it says, okay, I will exchange that. Whereas on the lower part, we actually see a post to search PHP, which might reflect back this password. In this case, our extension checks, hey, login PHP is not search PHP, so I will not insert the password here. We then did a functional evaluation, and this is where I come back to the 325 domains we had seen earlier that somehow used JavaScript to access the password fields. So almost 230 of these domains actually just went ahead and checked whether there was some password there or not. And if you clicked kind of submit or log in without the password being there, this is an alert box saying, hey, you don't try to send this form if you don't have a password. 96 domains actually sent the password via XML HTTP requests rather than posting this form. And out of those, actually 23 domains hash the password before sending it out. And if you think about the fact that we inserted, rather than inserting a password, we inserted this nonce. If you hash the nonce, we have no way of seeing it in the outgoing request because we actually don't know what kind of hash function is being used. So in these cases, our implementation breaks because the password manager inserts the nonce is hashed, and it doesn't match the password that is stored on the server side. One domain, for some reason, went way out of its way to be super secure and used base64 encoding or encryption, I think they called it. Again, this causes issues because you base64 encrypt the nonce. And 6 domains out of those actually send passwords in get parameters. So in total, 30 of these domains that we looked at would break with our approach. Which means that 98.6% of all the domains we analyzed would work perfectly fine with what we propose. And also, more importantly, actually storing passwords for these XML HTTP requests is currently not supported by browsers because browsers wait for a kind of a form to be submitted to, so basically a post or a GET request that is initiated by this form submit. And XHR is not a form submit. Okay, then concluding. what should you take away from this talk? So the current generation of browser-based password managers is quite vulnerable. And even if most of you, and now I can say this because I'm slowly taking off my Microsoft hat, I'm not a big fan of IE for several reasons. But although most people kind of hate it and say, hey, this is a really bad browser, in this instance, it's actually very, very secure. Then a very shocking thing that we found is that almost half of the passwords are actually posted via HTTP, which is, it makes the job for an attacker, for a network attacker, quite easy because you can just go ahead and read those from the outgoing request. And at least against a cross-scripting attacker, we can do something. So we can actually relatively easily patch existing in-browser solutions to allow for these, for defending against these kinds of attacks. It's harder against network attacker. What we can do is, for example, enforce that passwords should always be sent via HTTPS rather than HTTP. But then again, we would, in theory, break half of the websites. Okay, and with that, I'd like to thank you very much for your attention. You want to take a picture, and we're happy to take any questions you might have. Need to put the cat picture back on. I think we will put the slides on our domain, which is here. So the advertisement comes at the end.
There's a question?
Yeah, so is there a difference between IE versions or open versions?
Actually, there is. So this initial research we conducted was, I think we did it kind of end of last year. And wait, let me quickly go back to that slide. This is all screwed up. This one. Okay. So as an example, this I think initially was Safari 7.0, which didn't have user interaction. Now 7.1 has user interaction. For Chrome, we did the initial tests kind of with Chrome 31, I think. Now we're up to 37, I believe. So they are, while the browsers change, they actually become somewhat more secure. I can't really say it for Opera right now. I don't know that off the top of my head. But IE was always 11, I believe. So. Okay. Yeah?
You talked a lot about the security of the behavior of the password managers. I'm wondering whether you also have some insight about the security of the persistency.
Okay, so. Okay, so your question is basically, while we looked at how they behave, we didn't really analyze how securely they store the passwords, because there has been a lot of research going on before into this. I couldn't really say. I think I know something about Firefox, but I mean by default, none of them actually have passwords that secure their keychain. So you have to actually know what you're doing to add kind of a password protection to your keychain or your password manager's database. So there's nothing in there.
I think it also depends on the operating system. For example, in macOS, most of the WebKit browsers use the keychain of macOS, so they store the password securely in there. But on other operating system, it's different.
Proposing is basically like the password manager should be like a proxy. Because in theory, I could, with JavaScript, I could like catch the get a post request and say, look, just before you actually do the request, you've got stuff to do.
Okay, so what you're saying is we propose to use this kind of as a proxy where we store this nonce, but JavaScript could, in theory, access the outgoing request. But actually, this kind of mangling with the outgoing request is done inside the browser after the form is submitted, where JavaScript has no way of accessing the page anymore. So the request is already outgoing, and JavaScript just sees, okay, it might notice there is a request going out, but actually there's no way of kind of accessing this mangled request that we did. Okay. So it's secure by this.
So it's currently not possible to access the request on the way to the server for JavaScript. So there's something called service workers where you can install JavaScript to request, but I think this is happening before. So we are sitting in the browser on a much deeper level than JavaScript is accessing.
There's moments where I I'm a bit confused because, well, personally, because I really don't know too much about JavaScript anymore. It used to be possible to like manipulate the request almost to the full extent.
But only in extensions.
Yeah.
So not in JavaScript running in a web page.
Actually, extensions are basically JavaScript, but they are kind of running as an extension in the browser backend rather than something you can access from the website. So there's no XSS towards extensions. Well, there is sometimes, but you need a crappy extension to begin with. Okay.